Look up at the surface of a pool from underwater, and you might notice something strange. That invisible boundary between water and air can act as a more perfect, efficient mirror than polished silver. When light hits a boundary between two different transparent materials, it splits. A fraction of the light bounces back as a reflection, while the rest pushes right through and bends, a process called refraction. But a unique physical trap emerges when light travels in a very specific direction, originating inside an optically denser material, like water, and moving toward a less dense, rarer material, like air. This diagram shows how that interface normally behaves. Light from an object at a real depth, labeled H2, bends as it hits the air, creating a shallower apparent depth, labeled H1. This diagram shows the defining rule of this upward journey. Moving into a less dense medium forces the light to bend away from the normal, that dashed vertical line sitting perfectly perpendicular to the surface. Because the escaping light bends away from the vertical, it is forced down, pushed closer and closer to the horizontal boundary line itself. This geometry sets the stage for a mathematical breaking point. Imagine placing a laser pointer underwater and slowly tilting it, steadily increasing the angle at which the beam strikes the surface from the low. At steep angles, light escapes, bending towards the surface. Tilt further, and the escaping ray drops dangerously close to the waterline. Eventually, the beam is forced to exactly 90 degrees, grazing the horizontal boundary. Physicists call this the critical angle, I sub c. What happens if you tilt the laser a fraction of a degree past that critical angle? Snell's law cannot be satisfied. Refraction becomes mathematically impossible, and 100% of the light energy ricochets directly back down into the water. Total internal reflection differs from the partial internal reflection seen earlier by its absolute containment of light. Zero energy escapes across the boundary. Even high-quality silver mirrors absorb a percentage of the light that hits them. A boundary undergoing total internal reflection reflects light perfectly, with zero loss. By simply changing the angle, a transparent surface that freely transmits light becomes an entirely impenetrable barrier. This diagram shows the equation governing this trap. The sign of the critical angle equals N21, a constant representing the relative optical density of the two materials. Every material has a different geometric trapdoor. In water, you have a relatively wide margin. You have to tilt the light to about 49 degrees before it gets trapped. Glass is denser, restricting that escape window down to 41 degrees. This table compares the critical angles for various media, and you can see the extreme case at the bottom, diamond. Because of its massive refractive index, its critical angle is an incredibly tight 24.4 degrees. This low threshold is exactly what gives gemstones their sparkle. Light easily enters the top of a cut diamond, but once inside, it finds it nearly impossible to strike an interface at an angle small enough to escape. Instead of passing straight through, they bounce against internal walls, multiple times, gathering and mixing, before finally finding an exit. The brilliant fire of a diamond is simply the visual result of light caught inside a highly efficient geometric trap. We've taken this natural quirk of physics and engineered it into a structure designed to carry information over thousands of miles, the optical fiber. This diagram shows the architecture. A high-density glass core sits inside a lower-density glass cladding, ensuring the light trap is always active. When a light pulse enters the core, it strikes the outer walls beyond the critical angle, ricocheting and zigzagging indefinitely. Because the light is continually bouncing inward at such shallow angles, you can bend or knot the physical fiber, and the light simply follows the internal path. Unlike electrical signals in copper wire that bleed energy as heat, light traveling through these perfectly mirrored glass walls experiences a nearly lossless journey. Total internal reflection, a simple quirk of geometry at the boundary of two materials, is the exact physical mechanism that allows us to pipe the collective knowledge of the world across oceans at the speed of light.